Characterizing Subtractive Ideals in the Finite Semirings B sub n, I by Chloe Williams. My faculty sponsor is Dr. Francisco Alarcon. Abstract. It is well known that every ideal in a ring is subtractive or the kernel of a homomorphism. This is not necessarily the case for the ideals of semirings. In this work, we seek to give a simple numerical characterization for the subtractive ideals of a large class of finite semirings, denoted B sub n, I, that can be considered as generalizations of the integers mod n. My hypothesis is that for the finite semiring B sub n, I, where x is an element of the positive integers and x is greater than n, less than n, we assume a is the greatest integer possible, such that ax is less than or equal to n is less than a plus 1 times x, and ax plus I equals n. Then the subtractive ideals of B sub n, I are principal ideals of the form 0, x, 2x, 3x, ... up to ax, which can be written as the principal ideal generated by x. So this is my introduction. Here I have the definition of commutative rings. A commutative ring is a non-empty set R equipped with two operations, usually written as addition and multiplication, that satisfy these 9 axioms: the closure for addition, associative property for addition, commutative property for addition, additive identity, additive inverse, closure for multiplication, associative property for multiplication, the distributive laws, and the commutative property for multiplication. Some examples of commutative rings are the set of all real numbers, the set of the integers, and the set of the integers with addition and subtraction mod n, where n is an element of the positive integers. Commutative semirings. A commutative semiring is a non-empty set R equipped with two operations, usually written as addition and multiplication, that satisfy these following axioms: closure for addition, associative property for addition, commutative property for addition, additive identity, closure for multiplication, associative property for multiplication, distributive laws, commutative property for multiplication, and absorption property. Some examples of commutative semirings are the set of all natural numbers, the set of all non-negative real numbers, and B sub n, I, which equals 0, 1, 2, 3, ... up to n minus 1, with n is greater than 1, 0 is less than or equal to I is less than or equal to n minus 1, and operations determined by x plus 1 equals x plus 1, if 0 is less than or equal to x is less than n minus 1, and n minus 1 plus 1 equals I. Ideals. An ideal for a ring is defined such that R is a ring and I is a subring of R. I is an ideal of R if and only if for any R is an element of R and A is an element of I, then AR is an element of I and RA is an element of I. Ideal for a semiring. A subset I of a semiring R is an ideal if I is closed under addition and multiplication, and for any lowercase r element of uppercase R, I element of uppercase I, we have that Ri is an element of uppercase I, and IR is also an element of uppercase I. Subtractive ideals. Properties of ideals. Subtractive property for the ideal of a ring. If J is an ideal of a ring R, if A is an element of J, and A plus B is an element of J, we must have B as an element of J as well. A principal ideal. Let R be a commutative ring with identity, and lowercase r is an element of uppercase R. Then the ideal I equals RC for every C in R is the principal ideal generated by lowercase r. Now we will look at some examples of B sub n comma I and their ideals. Example 1. We consider the semiring B sub 5 comma 1, which is the set of integers from 0 to 4, where 4 plus 1 equals 1. When we look at the properties of this semiring, we have that J, which in this case will be 0, 2, 4, is an ideal of this semiring. This ideal is subtractive because 0 is an element of R, 2 is an element of R, and 4 is an element of R. And the difference between two consecutive terms is 2, which is in R. Thus, J is a subtractive ideal. Now we look at the semiring. Now we look at the same semiring. J equals 0, 4 is an ideal of this semiring. 4 is an element of J, 0 is an element of J, and the difference between 4 and 0, which is 4, is also an element of J. So J is a subtractive principal ideal. Looking at the same semiring, we have that J, which equals 0, 1, 2, 3, 4, which is the semiring itself, is an ideal of the semiring. All the integers from 0 to 4 are in this ideal, and the difference between two consecutive terms is 1, which is in this ideal. So this ideal is subtractive in principle. J equals 0 is also an ideal of this semiring. And this ideal only has the element 0, so it must be subtractive. It is also the principal ideal generated by 0. J equals 0, 2, 3, 4 is an ideal. 2 is an element of J and 3 is an element of J, but 3 minus 2 equals 1 is not an element of J. So the ideal is not subtractive. Now we look at different semirings. First we will look at B sub 6 comma 3, the integers from 0 to 5, where 5 plus 1 equals 3. J equals 0, 3 is an ideal of this semiring. 3 is an element of J and 0 is an element of J, and the difference between those two terms is 3, which is also an element of J. So this ideal is subtractive. It's also the principal ideal generated by 3. Finally, we will look at the semiring R, which equals B sub 10 comma 0, which is the integers mod 10. J equals 0, 2, 4, 6, 8 is an ideal of R. All elements in this ideal are even, so the difference between consecutive terms is 2. So this ideal is subtractive, because 2 is in this ideal. The characterization of subtractive ideals in B sub n comma I. First, we need to define sums in B sub n comma I. So we will show algebraically why our hypothesis is true. Let us assume that one of the subtractive ideals of B sub n comma I is of the form m, which equals 0x, 2x, 3x, up to ax, where ax equals n minus I. The properties of addition plus 1 in the semiring B sub n comma I follow this pattern. Now we will look at the properties of addition to confirm that this set n is subtractive and is an ideal. 0 plus x equals x, x plus x equals 2x, 2x plus x equals 3x, 3x plus x equals 4x, and so on up to x times a minus 1 plus x equals ax. Now we must find ax plus x and prove that it equals x in the semiring. We are given that ax equals n minus I in the ring, and n minus 1 plus plus 1 equals I. Thus, ax plus I minus 1 equals n minus 1, as defined by the semiring. This gives us that ax plus I equals I in this ring. To find ax plus x, we rewrite it as ax plus I plus x minus I. Since ax plus I equals I in the semiring, we substitute here to get ax plus x equals I plus x minus I equals x. We now have that ax plus x equals x. Since each term is a multiple of x and is less than n minus 1, each pair of terms must have a difference that is less than n minus 1 and a multiple of x, so it must be in the ideal. Thus, this ideal is subtractive and is a principal ideal generated by x. Now, if an ideal does not consist of the multiples of an integer x in the semiring, it will not be subtractive. This is because, as shown above, bx minus cx equals b minus c times x, where b and c are both integers. But if one element is not a multiple of x in the ideal, then bx plus c minus dx equals b minus d times x plus c. Not all elements will be in the ideal. Also, if we take a value in the original semiring and multiply it by a value that is c mod x, where c is a positive integer, c is less than x, the result will not always be a value c mod x, so the ideal will not be guaranteed to be subtractive. The only way for an ideal to be guaranteed to be subtractive is if all values in the ideal are a multiple of a positive integer. In this case, the elements are not guaranteed to all be a multiple of an integer. So the set may be an ideal of the semiring, but it will not be a principal subtractive ideal. Let us now examine the semiring b sub n comma I and assume that its ideal is f, which is the set of integers from 0 to n minus 1, but excluding 1. n minus 1 minus n minus 2 equals 1, n minus 2 minus n minus 3 equals 1, and up to 7 minus 6 equals 1, 6 minus 5 equals 1, 5 minus 4 equals 1, and 3 minus 2 equals 1. But 1 is not in f, so f cannot be a subtractive ideal. Let's now assume that the semiring is b sub nx minus 1 comma I. And the ideal is written as g, which equals 0, 2x, 3x, 4x, up to n minus 1x and nx. We know that n minus 1x minus n minus 2x equals x, and n minus 2x times x minus n minus 3 times x equals x, up to 3x minus x equals x. Or, excuse me, 3x minus 2x equals x. However, x is not an element of G, so this ideal is not subtractive. Now we're going to create a proof by induction of our hypothesis. Our hypothesis states that for a finite semiring, b sub n comma I, x is an element of the positive integers, where x is less than or equal to n. We assume ax is less than or equal to n is less than a plus 1 times x, and ax plus I equals n. Then the subtractive ideals of b sub n comma I are of the form 0, x, 2x, 3x, up to ax. If a semiring has an ideal that is non-principal, it will not be subtractive. So now we will examine the proof by induction. So for the base case, I made two charts, and here's the key for the charts. So the sums in b sub n comma I. This would be the value a in b sub n comma I, and this is a plus 1 in b sub n comma I. So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, up to I minus 1 plus 1 equals I. But then I plus 1 is I plus 1, up to n minus 1 plus 1 equals n, and then n plus 1 equals I. This pattern in orange will repeat, but the red up here will not repeat. Here, which will be on the side of our chart, is the b sub n comma I written in this way, and then the ideal 0x would be written like this. So here is our base case chart 1. So b sub 6 comma 0, 6 comma 1, up to 6 comma 5, each with their respective subtractive ideals. So we see examples of all possible semirings of the form b sub n comma I. So first, let's examine b sub n comma I when n is 6, which was in the previous slide. So when n equals 6 and I equals 0, n minus I equals 6, and 2 and 3 are divisors of 6. So two examples of possible ideals are 0, 2, 4, and 0, 3. When n equals 6 and I equals 1, n minus I equals 5, and 5 is a divisor of itself, so the possible ideal here is 0, 5, which is also the principal ideal generated by 5. When n equals 6 and I equals 2, n minus I equals 4, and 2 is a divisor of 4, so one example of a possible ideal is 0, 2, 4. N equals 6 and I equals 3, n minus I equals 3, and 3 is a divisor of itself, so one example of an ideal is 0, 3. When n equals 6 and I equals 4, n minus I is 2, and 2 is a divisor of itself, so a possible ideal is the principal ideal generated by 2. When n equals 6 and I equals 5, 1 is a divisor of 1, which is n minus I, so an example of possible ideal here is 0, 1. Here is the second base case chart for when n equals 7. Here we have b sub 7 comma 0, b sub 7 comma 1, up to b sub 7 comma 6. And in red font here is shown their principal ideals. Now we will look at b sub n comma I when n is 7. When I equals 0, n minus I is 7, and 1 is a divisor of 7, so one possible ideal here is 0, 1. When n equals 7 and I equals 1, n minus I equals 6, and 6 has divisors of 2 and 3, so two possible ideals here are 0, 2, 4, 6, and 0, 3, 6. When I equals 2, n minus I equals 5, so one possible ideal here is 0, 5. When I equals 3, n minus I equals 4, and 2 is a divisor of 4, so one possible ideal is 0, 2, 4, 6. When I equals 4, n minus I equals 3, and 3 is a divisor of itself, so an example of a possible ideal is 0, 3, 6. When I equals 5, n minus I is 2, and which is the divisor of itself, so a possible ideal here is 0, 2, 4. When n equals 7 and I equals 6, n minus I equals 1, which is a divisor of itself, so one possible ideal is 0, 1, 2, 3, 4, 5, 6, 7, which is the semiring. Now, let's assume the hypothesis is true for all I, n, and x. And now we must prove true for n plus 1 and I. We have that for any n and I, the set of subtractive ideals must have elements that are multiples of divisors of n minus I. And now we must show this for n plus 1 and I. So assume that I equals 0. The set b sub n plus 1 comma I is equivalent in this case to b sub n plus 1 comma 0, or the integers mod n. If y is a divisor of n plus 1 minus I, or n minus 1 in this case, Since summing them will still be a multiple of x, it will be in the integers mod n. Any other value that is a multiple of x will have a remainder that is a multiple of x when it is taken mod n. It also has the subset of 0, y, 2y up to dy, where d is also a divisor of n plus 1 minus I. Now we assume that this is true for all I from 1 to n. And now we are showing that the hypothesis is true for I. We have 0 plus 1 equals 1, 1 plus 1 equals 2, up to n minus 1 plus 1 equals n, and n plus 1 equals n. The set contains the element n, so this works. N is a multiple of 1. In this case, n plus 1 minus I equals n plus 1 minus n, which equals 1. The set is also a principal ideal, which is generated by x. So every value in this set must be a multiple of 1, because in this case, x would equal 1. Thus, for any n sub I, the ideals must be of the form 0, x, 2x, 3x up to ax, which is equivalent to the principal ideal generated by x. We can also consider the ideal j, which equals 0, 2, 3, 4 up to n. This ideal is not subtractive because 2 and 3 are elements of j, but 3 minus 2 equals 1 is not an element of j. This ideal is not principal, but if 1 is appended to the set, it becomes a principal ideal generated by 1. Since this new ideal contains all elements of the original semiring, it is subtractive. And we finished the proof.